Bismillah. Welcome to Think Math. In this lesson, we connect four ideas: powers, roots, rational exponents, and exponential equations. Our aims are simple. First, we study the roots of x to the n equals a in the real numbers. Second, we define rational exponents using nth roots. And third, we use all of this to solve basic exponential equations. We already know how to raise a number to a power. Now we are going to reverse that process. 2 cubed is 8, and going backwards, the cube root of 8 is 2. So a root simply undoes a power. And in a moment, we'll see that a rational exponent is just a compact way of writing that same idea. Let's build some intuition before we get formal. On the left, a square root. The square root of 9 is 3, because a square whose side length is 3 has an area of 9. On the right, a cube root. The cube root of 8 is 2, because a cube with edge length 2 has volume 8. Roots measure what side length gives this area or volume. Not every equation of the form x to the n equals ae behaves the same way. So here's a compact decision chart. If n is odd, there is exactly one real root, no matter what a is. If n is even and a is positive, there are two real roots, plus or minus the nth root of a. If n is even and a equals 0, there is exactly one root, x equals 0. And if n is even and a is negative, there are no real roots at all. An even power can never produce a negative result. This is the same idea as saying, if a to the n equals b to the n, and n is odd, then a equals b. But if n is even, then a equals plus or minus b. Let's put that chart to work with three quick examples. Example 1. 3x to the fifth equals negative 96. Dividing through x to the fifth equals negative 32, and since 5 is odd, there is exactly one real solution, x equals negative 2. Example 2. X to the sixth equals negative 64. 6 is even, and an even power can never be negative in the real numbers. So the solution set is empty. X minus 2 to the fourth equals 81. And 81 equals negative 3 to the fourth, or 3 to the fourth. Since the exponent is even, x minus 2 equals plus or minus 3, giving x equals 5 or x equals negative 1. Example 4. The cube root of x squared equals 1. Cubing both sides, x squared equals 1, so x equals plus or minus 1. Example 5. The fourth root of the quantity 3x plus 2 cubed equals 8. Raising both sides to the fourth power, 3x plus 2 cubed equals 4096, which is 16 cubed. So 3x plus 2 equals 16, giving x equals 14 thirds. Roots also follow two useful rules for products and quotients. The nth root of a times b equals the nth root of a times the nth root of b. And the nth root of a over b equals the nth root of a over the nth root of b, as long as b isn't 0. For example, the cube root of 8 times 27 splits into cube root of 8 times the cube root of 27, which is 2 times 3, or 6. And the square root of 49 ninth splits into 7 thirds. Two mistakes come up again and again, so let's flag them clearly. First, the square root of x squared is the absolute value of x, not simply x, because the principal square root is never negative. Second, the square root of a sum is not the sum of the square roots. For instance, the square root of 1 plus 3 is 2, but the square root of 1 plus the square root of 3 is not 2. Root rules don't distribute over addition or subtraction. Now, let's derive rational exponents from scratch. Start with x squared equals a. Raise both sides to the 1/2 power. x equals a to the 1/2, which is the square root of a. The same reasoning works for any m. Starting from x to the n equals a. Raising both sides to the 1 over n power gives x equals a to the 1 over n, which is the nth root of a. And extending this, a to the m over n equals a to the 1 over n raised to the m, which is the nth root of a, raised to the m, or equivalently, the nth root of a to the m. So remember, the denominator of the exponent gives you the root, and the numerator gives you the power. Let's state this as a clean set of rules. A to the 1 over n equals the nth root of a for any positive integer n. A to the m over n equals the nth root of a raised to the m, which equals the nth root of a to the m, where m and n are integers and n is greater than 1. For example, 16 to the 3/4 is the fourth root of 16 cubed, which is 2 cubed or 8. And 27 to the 2/3 is the cube root of 27 squared, which is 3 squared or 9. Let's put that rule straight to work with two equations that both need it. Example 6. The quantity x squared minus 4x minus 13 raised to the 3/5 equals 8. Raising both sides to the 5/3 power, x squared minus 4x minus 13 equals 8 to the 5/3, which is 32. That gives x squared minus 4x minus 45 equals 0, which factors to give x equals 9 or x equals negative 5. Example 7. X to the 4/3 equals 27. Rewriting the exponent as a root and a power, that's the cube root of x raised to the 4th equals 27. Taking the 4th root of both sides, the cube root of x equals plus or minus 27 to the 1/4. So, x equals plus or minus 27 to the 3/4. Both of these examples apply the rule we just introduced, using it to solve rather than just to simplify. With these rules, we can simplify more complicated radical products. Example 8, the 5th root of a cubed times the square root of a cubed, converting to exponents, that's a to the 3/5 times a to the 3/2, which adds to the 21/10, or a squared times the 10th root of a. Example 9, the cube root of x squared times the cube root of x squared. Both pieces equal x to the 2/3, so multiplying gives x to the 4/3, which is x times the cube root of x. Example 10, the cube root of a to the negative 5 squared times the 4th root of a cubed. That's a to the negative 10/3 times a to the 9/4, giving a to the negative 13/12, or 1 over the 12th root of a to the 13. Now let's solve exponential equations using these same tools. Example 11, 2 to the x plus 5 equals 8. Since 8 is 2 cubed, we match exponents. X plus 5 equals 3, so x equals negative 2. Example 12, 3 to the x squared times 3 to the x squared minus 4 equals 1. Adding exponents gives 3 to the 2x squared minus 4 equals 3 to the 0. So 2x squared minus 4 equals 0, and x equals plus or minus the square root of 2. Example 13, 4 to the x plus 2 equals x to the x plus 2. Either the exponent x plus 2 is 0, giving x equals negative 2, or the bases must be equal, giving x equals 4. So the solution set is negative 2 and 4. Example 14, 4 to the minus 3 equals 3 to the 2x minus 6. Rewriting 4 as 2 squared, we get 2 to the 2x minus 6 equals 3 to the 2x minus 6. Since 2 and 3 are different bases, this can only hold when the exponent itself is 0. 2x minus 6 equals 0, so x equals 3. Two more slightly trickier exponential equations. Example 15, 2 to the x times the cube root of 4 equals the cube root of 16. Inverted, Converting everything to base 2, 2 to the x times 2 to the 2/3 equals 2 to the negative 4/3. Matching exponents, x plus 2/3 equals negative 4/3, so x equals negative 2. Example 16, 4 to the x squared minus 1 equals 8 to the negative x. Rewriting in base 2, 2 to the 2x squared minus 2 equals 2 to the negative 3x. This gives 2x squared plus 3x minus 2 equals 0, which factors as 2x minus 1 times x plus 2 equals 0. So x equals 1/2 or x equals negative 2. Before we finish, pause and test yourself with 3 quick questions. How many real solutions does x to the 4th equals 16/2? How would you rewrite a to the 3/5 using a root? And why isn't the square root of x squared simply equal to x for every real number x? Pause the video now and answer these before moving on. To finish, here are 3 exercises for you to try on your own. Number 1, solve 3 to the 3x plus 3 to the 2x plus 3 to the x all over 3 to the 2x plus 3 to the x plus 1 equals 1/9. Number 2, solve 2 to the x plus 1 plus 2 to the x minus 1 equals 5. Number 3, solve 5 to the x plus 125 over 5 to the x equals 30. Pause the video and work through these carefully on your own. Thanks for watching and see you in the next lesson.